This is page 2 of the memory allocation notes. So when we have new memory from sbreak, that is terrible writing, sbreak, or if we have freed memory, so when you return the memory through calling free, both of these are added to the free list. So let's talk about the free list. So chunks. So when you have new memory, it gets divided into chunks as there are new calls to malloc, and then these chunks are returned when you call free, and the chunks are stored in what are called bins, which are just linked lists. So what you have is an array of linked lists because there's bins for different size chunks. So I'm going to try to draw you a picture of what this looks like. So it'll be fairly long. This probably isn't long enough, but we'll start with that. And so the size of the first bin is 16, and that is a linked list of bins that are exactly 16, that have chunks that are exactly 16 bytes each, and then 24 bytes, and some of these bins will be empty, some won't. So let's say that bin 32 has one chunk in it. The difference between these bins is 8 bytes. So as you go up, each bin is 8 bytes bigger. So we have bins for blocks of up to size 512. So let's make this a list with 2. And these bins are exact sized bins. So each chunk is exactly either 16 bytes, 24 bytes, 32 bytes, 40, 48, and so on up to 512. And so we have a total here of 64 bins. If you do the math, that should add up to 64. So after that, the bins are not exact size. So a bin will hold something up to, will have chunks up to the size that's represented. So these are going to be increments of 64 now, between 64 bytes between the bins. So let's just say that that also has two chunks in it, and then 576 plus 64 should be 640, and this goes up to 2560. So that's plus 64, the difference between those bins is plus 64, and we have 32 of these bins, and I'll add the information about them being sorted bins after, but basically in the 576 bin you'll have chunks that are anywhere from, I guess, 512 plus 8, so 520 up to 576, and so on. And let's just draw a dividing line. So there's one set, there's another set, and now the increments get bigger again. So these are going to be increments of 512. So 2560 plus 512 should be 3072. So the increment there is plus 512, and this goes up to bins up to 10,752, which is probably 10 kilobytes. So we have 16 of these bins, and so on. Actually, let me draw the line first. So, and then, so let's extend this down a little bit. So we will have 8, I'll do this in green. So we'll have 8 of increments of 4 kilobytes, or 4096, and then we'll have 4 bins that have increments of 32 kilobytes. So that would be 32,768. And then we'll have 2 bins that are increasing in size by 256 kilobytes. And then there's 1 bin, and this is whatever's left. And so basically what we'll have here is a pointer to the new memory from the S-break call, and then that gets chunked up to satisfy calls to Mem Alloc. So these bins are what are called the sorted bins. So we had exact sized, these are sorted bins, and so like I said before, in the 576 bin you can have chunks that are 520, 528, up to 576, and they're stored in that. It's a doubly linked list, and they're stored in that list in sorted order. So when you're traversing it, it's basically linear time. It uses some tricks to speed that up a little bit. So that's enough information on the bins. If a right sized chunk isn't found in the free list, Mem Alloc will split off a chunk from the unused memory. That's in the box here, the unused space, and that's the last bin in the list. And if it can't find one there, then what it will do is it will use the best fit. So it will go to say you want like a 5 kilobyte chunk, and what's left isn't big enough to satisfy that request, then it will go to the 32 kilobyte bin and choose the smallest one that it can find that will hold 5 kilobytes, even if it's not exactly the right size.